here at National Yat-sen University in Kaohsiung. It is our great pleasure to have you all with us uh, for this 2 days of deep dive into the future of wireless communications. So this workshop will try to bring together leading researchers to explore how 6G will integrate artificial intelligence, quantum technology, advanced antenna architectures, and semantic and near field communication into intelligent wireless systems. Over the next 2 days, we will hear about pinching antenna systems, RIS added links, wireless quantum code design, semantic communications, and many other topics that are rapidly moving from theory to practice. So here in this workshop, we have total 8 speakers. Um, so our first speaker is Professor Zhiguo Ding. He is a professor in communication at the University of Manchester, UK. Um, he, he is also a distinguished adjunct professor at Khalifa University, as well as academic visitor at Princeton University. He is a fellow of the IEEE and Web of Science, highly cited researcher in multiple disciplines. With research spanning 6G networks, non-orthogonal multiple access, energy harvesting networks, and statistical signal processing. So Professor Ding has served as a area editor or editor for leading IEEE journals, such as IEEE Transaction on Communications, Transaction on Wireless Communications. He has received prestigious awards, including the IEEE Heinrich Hertz Award and the IEEE Vehicular Technology Society Jack Newberger Memorial Award. His keynote today on pinching antenna systems reflect his continued leadership in shaping advanced multiple access and transceiver architecture for 6G and beyond. Let's welcome Professor Zhiguo Ding for his talk. Yes.
Right. First of all, I really appreciate Professor Keshav for organizing this workshop. Right. Thank you. Right. So, so today we're going to talk about pinch antenna. I think you can treat this as like the first part. I think.
Yes.
Thank you. Thank you. Can you hear me? Okay. Good. Thank you. Then. So I will cover the. You can. So Yuan Wei is going to cover another part. I think tomorrow. So for my part, what I want to introduce first is the motivation. So why we want to study pinch antennas. Then we are going to have a few examples about the basic principles of pinch antenna. Then one of the things we are very excited nowadays is actually this concept of pinch antenna can be generalized. Not just for high frequency dielectric waveguide based pinch antenna, you can also go low frequency, and that's what we're going to talk about. Antenna placement, that's something I'm not sure, maybe I can skip, and then I will spend a lot of time for this environment division multiple access. Then we're going to talk about the research challenges and the conclude talk. to motivate you to feel that this is something interesting. So that actually there are quite a few ways to provide motivation. One is a futuristic way. Is essentially is the question: what kind of communication links should we want to provide in the future? Essentially, I think we can say that three things. One is we want to provide a fiber link, which actually can give us a fiber connection. Because fiber connection is probably the best we can ask. It's very reliable, data rate is high, and then also secure. Meanwhile, we also want this future wireless link should be user-centric in the sense that if you watch those sci-fi movie, you saw those com device actually is really moving with the user, right? So the central user-centric. That actually is something fiber link cannot be accommodated because we need to you need to connect device with a fiber connection. That's not possible. Now, on top of last but not least, we want links, wireless links should be cheap in the sense that they should be provided with a low cost. So that is some three things that we want to, three criteria we want to provide for future wireless link. Now, another way to motivate. Thank you. Another way to motivate this pinch antenna essentially is if we go look at this famous Shannon formula, we can say most of communication techniques proposed recently are motivated by this simple formula. For example, MIMO essentially is focused on this parameter in front of logarithm. Essentially, this is bandwidth. Right. So by using MIMO, we created these separate SYSU channels. Then essentially, we multiply. So for example, if we have 2 by 2 MIMO, essentially we created these two separate SYSU channel. We increase our bandwidth twice. NOMA, I think many of our colleagues know me because we work on NOMA, and so NOMA essentially focuses on these two parameters. But NOMA also focuses on bandwidth, also transmit power. So, for example, take a power domain NOMA as an example. Essentially, we focus on power domain, different user given different transmit power, right? So transmit power, and meanwhile also encourage users to share the same bandwidth. So that's the reason we're saying NOMA is actually focused on two parameters. In this parameter, in this formula, there are two more parameters we have not talked about. Even for noise power, that is something sounds very like should be fixed, not something we can control. Recently, there are another technology called noise modulation, which is essentially to try to reconfigure that parameter. So what left in the Shannon's formula is channel. Conventionally, we don't really talk about the reconfigure channel because channel is given. Wireless environment is given. It's not something we can play, can tune. However, we generally believe that we are in the middle of a revolution. In the sense that we think channels can be changed, can be tuned for tailored for our communications. So here we list a few examples for flexible antenna, which essentially is to reconfigure channels. Take a RIS example. So the original motivation to develop RIS is, let's say we have a line side blockage between transmitter and receiver. So I'm going to deploy a RIS. And so this RIS essentially provide a reflect line of sight between the transmitter and receiver. However, RIS actually suffer this issue with we want to take time. Thank you very much. So essentially, The drawback of RIS is this double attenuation. So for example, from the transmitter to RIS, you're going to have this one attenuation, right? And from RIS to the receiver, you have another round of attenuation. Now, for those who run the MATLAB simulation for RIS, you probably notice that if you compare line sight between transmitter and receiver to that created the reflect paths between transmitter and receiver through RIS, these two paths, right, the strength can be significantly different. So if you have line sight, in many cases, you probably find out that the effect to tune those the reflecting elements is not that significant because line sight is much stronger than this reflect path. All right, so that is the reason. At least that is the. I think that is the first step to we try to reconfigure environment. Fluid antenna, move antenna, they based on the same idea. So they, let's say as a transmitter, I implement fluid antenna or move antenna. Then the antenna there, a transmitter can be wiggled, moved in a small scale, maybe centimeters. Then what they are doing is still in a context of conventional MIMO context. So, for example, if you have deep fading in one position, right, and by changing my antenna for small scale, let's say a few centimeters, then we're going to create a favorable multipath fading. So in that sense, you can say fluid antenna, move antenna are very useful if we have if we do not have a line sight. Then by using these two types of antenna, you can create a favorable small scale fading. Right? Then you have, but again, if you have a line sight, then if you compare line sight with those we call the non-line sight parts, right? The strength is the difference between these two is significantly significant. For example, the line sight is really strong. So, however, if we do not have a line sight between transmitter and the receiver, by using fluid antenna and move antenna, you will not be able to create line sight. The reason is following. For example, I mean, let's say between me and Professor Keshev, we have a partition, right? Between us, there's a partition. This partition essentially block line of sight between me and the Professor Keshev. Then now, if I using fluid antenna, move antenna, I'm going to just to change my position for let's say a few centimeters. And that will not help for create a line of sight, right? I have to move in a large scale, few meters, to then in that case I will have that line of sight. Now for that, both fluid antenna, move antenna cannot do, because you probably heard about that. For example, the best application scenario for fluid antenna essentially is in handset. So in your handset, you have a fluid antenna, then those antennas moving in different ports, right? Within a few centimeters, create a favorable small scale fading. That will not useful to create a line of sight. So today, most part of my talk is about the line of sight. We will see. On top of that, we also list a few interesting we want to ensure this what we should have. One is we said previously that we said the future wireless link needs to be cheap, practical, right? And however, if you look at those RIS panel, let's say 1024 by 1024, and it is very expensive to build. For fluid antenna, you have these ports on. Sounds very complicated. So that is something the current, so basically the cost. Another drawback is how to reconfigure the array. For example, let's say I already have this panel of reads 1024 by 1024. I want to add another 10. That's not possible because the panel is already configured. I cannot send the panel back to the factory, and that's just too complicated. Or I want to reduce the element. Similarly, for move antenna, full antenna, if you want to add or remove antennas, it's not as straightforward. Okay, so this is basically the motivation we had when we started to research for pinch antenna. Pinch antenna is a very practical thing, concept. Originally developed by Docomo. Now, if you look at their demo, they have a video, they have paper, they have some poster, and I recommend you to go to online to search those materials. But just look at the video, it's just amazingly simple. Right. So you have this dielectric waveguide, which looks like a cable. But for me, who is communication series, so I do not know much about this. But it seems like if you have the simply just use this is a closed pinch. That's something you have in home, and then simply tap it to your apply it on your waveguide. Then you basically you activated the antenna. Then there's a leakage of radio RF signals. Then you can say that okay, so the antenna is activated. There is a radiation of signal or energy. Then as a result, then there's a video, so the receiver gets some signal. Now, by simply release that closed pitch, then that signal is gone. So so basically adding or removing antenna or pinch antenna system is extremely simple. On top of that, what we're very excited is it provides a lot of flexibility for communication system in the sense that we have this dielectric waveguide, and you literally can activate your antenna anywhere along this waveguide, right? Then what is benefit? So okay, so we'll leave that in that. Okay, so then you can activate the antenna anywhere along this waveguide, and it's something related to it's more like similar to liquid wave antennas, right? But in a low cost way. We're going to repeat this many times today, so let's just go through this for now. What we think is the key feature of pinch antenna is able to support line-of-sight communications. That is a key difference between pinch antennas and mobile or fluid antenna. Right, so actually yesterday we had some discussion with Professor Keshav's group, right? And I was taught some students. I asked them to tell me, okay, what is the difference between fluid antenna and the pinch antenna, right? So I think you can say a lot, right? But essentially, the key difference is pinch antenna can support line-of-sight communications. So, for example, I'm very far from the base station, and there could be a lot of blockage. So that basically there's no line of sight. If my antenna is placed at the center of the service area, now I can simply just move antenna to the top on top of my head. In that case, I create this strong line of sight. Right. So that is something other and existing antenna system cannot provide. Line of sight. Actually, I have another motivation. I skipped some of you probably notice is the following. So you can say during the past, past 20 years, we have mainly been focusing on small scale, multi-pass fading. So MIMO, space-time coding. This is something, my PhD dissertation is about space-time coding. So essentially, okay, it's about to create a favorable fading and antenna simulation. The reason we are focusing on small scale fading, actually, it's because once there's a line of sight, actually, we simply give up the hope to have a line of sight. We said, okay, that's it. We accept the fate. Then we are going to focus on small scale fading, and we turn to those still important things, right? But okay, so however, if we know that a line of sight typically is 20 dB, which is 100 times stronger than non-line of sight. So, and before pinch antenna was invented, you can say there's no other techniques which can create a line of sight, right? So in that, we think Docomo's pinch antenna is out of box thinking. If there's no line of sight, we should create a line of sight, not to accept that the fate and do something else. Okay. Of course, there's other benefits for pinch antenna. For example, it's a very you can easily reconfigure your antenna array. You can remove, add your antennas. Also, you can support pinch antennas can be used to support a new form of MIMO, which I'm going to talk about in a minute. So this is part of, I'm going to briefly introduce how we can use pinch antenna in communication system. So the easiest way is following. So let's say we have two users here, right? And in the service area, and let's say we use a TDMA to, so one time slot, I'm going to serve this user. In that case, I'm going to activate my antenna in a position closest to this user. When another user is served, I'm going to move my antenna to another location to serve this user dedicatedly, right? So that is a simple way. I think that probably this is the first way to first step to implement pinch antenna. It's very simple, and you can if you have a single waveguide, you can also activate multiple pinch antennas. And so there's a trivial thing, which is how many antennas should we activate? So there's a trade-off. We're going to skip that. You can also use a TDMA, all right? So that's okay. And so, for example, when we serve this user, two antennas can be activated, served to this user. And then once this user is activated, is served, in that time slot, we can activate another set of antenna to serve that user. We mentioned NOMA, right? So pinch antennas can be used perfectly together with NOMA or support NOMA. Why is that? Because let's say I want to serve these two users simultaneously. So that means base station needs to send two signals to this user, to these two users. So these two signals essentially will be mixed in this waveguide. The signal sent by these two antennas essentially is just a phase difference, so it's more like analog beamforming. So you have a superposition of signals at transmitter. Then for many of us who used to work on NOMA, then immediately we thought, all right, we have a superposition at transmitter. Naturally, we should think about NOMA, and then you can, for example, do SIC at the receiver. Right? So that's the reason you saw there are quite a few works combine or apply pinch antennas to support NOMA. Okay, so MIMO. So you have multiple waveguides, multiple pinch antennas. I normally I don't like to show equations because that's boring, and this is early morning. We all very sleepy, so I try to make it very simple. So essentially, let's say you have two users. Then for one user, you have so-called signal to interference plus noise ratio, which essentially is a fraction. Numerator is intended user signal. Denominator is interference plus noise. Our objective is to increase the value of this fraction. To increase the value of a fraction, you have two ways. One is to increase the numerator. One is to decrease the denominator. The two principles lead to two famous concepts in communications. One is called zero forcing. Zero forcing essentially is to make sure that the denominator is minimized, essentially make sure this part is zero. So that is the smallest you can have for your denominator. Another way is to increase the numerator, so that it leads to MRC. Essentially, that maximizes your numerator. Traditionally, you have this dilemma. You can increase your, you have fraction. You can either increase your numerator or decrease your denominator. You cannot do both at the same time. You simply cannot. The reason is in this fraction, you can the only parameters you can play around is your pre-coding or beamforming. So then there's a limited things you can do. However, in pinch antennas, these channels can also be something you can play around. So that means now in your hand, you have two sets of cards to play. One is channel, the other is pre-coding. As a result, this upper bound, which basically is make sure that numerator is maximized and the denominator minimized. This upper bound, we call it holy grail because that we hope to achieve, but we'll never, during past, we will never be able to achieve that. Now, in the context of pinch antenna, this is something you can do. You can realize. Okay, so I'm going to skip the detail because we only need to grasp the idea in the concept. The details, if you're interested, you can read the papers. All right, so I think in the second half of this year, there are just things which make me excited, right? One is generalized pinch antenna, one is EDMA, and also we can talk about Professor Octavia. Also, her group did something called Y path. We can talk about that. These three things really make me. Oh, there's also segmented. Oh my God, these four things are very exciting. All right, so let's first talk about this generalized pinch antenna. Now, the motivation is I think there's maybe some of the audience, online colleagues need to mute their mics, otherwise we have this echo. Right, thank you. So we want to generalize pinch antenna because I think this concept is important, right? To make it more important, we need to make sure that this concept can be applied for low frequency, high frequency, indoor, outdoor. So then if we study or carefully examine this Docomo's pinch antenna, right? So we find out actually there are two stages for this Docomo's pinch antenna. The first one actually the communication through wire, cable, dielectric waveguide. That's quite interesting. So so the question is, if we want to generalize pinch antenna, we need to find another medium which is not dielectric waveguide. So okay, so that is one of the goals we need to accomplish. The second stage of pinch antenna is because the signal is leaked from the waveguide to free space. Then you have wireless the transmission or communication. The key thing for Docomo's pinch antenna for second stage is flexibility. So you have a cable and you can activate the antenna anywhere along that, right? So we need to make sure that if we have this concept of generalized pinch antenna, we still have that flexibility. Right? So how can we do that? Then we look around, all right? So then we found out actually, indeed, there could be multiple ways to generalize pinch antenna. The one way is so-called LCX, which is called the leaky coaxial cable. I think even for me, I think sometimes I feel I'm students. So when I talk to largers, right, those or King, they're or Professor Poole, from them, I feel I'm for sure it's a student, and a lot of things I never heard about. And when I talk to largers about pinch antenna, then this concept of leaky cable or leaky feed or LCX, right? And apparently this concept had been investigated many years ago. Then I went to IEEE Explorer and I searched LCX, and even in 1970s, in REE journal, so many of us do not even, many of you do not know REE, right, which is IET nowadays. They have some papers about this leaky feed, and they even use leaky feed to support vehicle communications. So that is 50 years ago. So leaky cable is following. So it's a cable, right? That is truly cable. It's a coaxial cable. So then you puncture holes on this cable. The signals can be leaked from those punctured holes, right? So in that case, if we go back to the first stage, using leaky cable, we can also to replace dielectric waveguide. Right? Second stage, unfortunately, a conventional leaky cable cannot support flexibility. But simple, if you have a way to plug a hole, and that basically stops signal leakage, right? And then you can also unplug a hole. Then you can create it, and then you can realize this flexibility using leaky cable. So that is one way. Another way is I actually saw some demonstration there in some universities. They are using, for example, metal pipe. The signal first goes through this pipe, but not inside the pipe. Actually, it's on the surface of the pipe. So that basically means the first stage, they are using the medium is no longer dielectric waveguide or leaky cable. They are using a simple low-cost metal pipe, right? And then you support the first stage. Then the second stage, essentially, you use active antenna. Then you can leak those signals to free space, so you can realize that wireless transmission. So both ways are fine, right? So just to recap, right? So you have dielectric waveguide. Docomo's demonstration, they use 28 gigahertz or even high. So that basically means you're going to use a high frequency, higher carrier frequency. You don't need the active antenna. So close pinch essentially is a passive antenna, right? So it could be used indoor, outdoor. Now for leaky cable, carrier frequency is low, below 6 gigahertz. So that basically needs a lot of good things. For example, in cable propagation loss is going to be very small compared to the high frequency one. Also, it can use it for outdoor. It's perfect for outdoor. I can give you this example. So leaky cable currently massively used for railway system and London Underground. For London Underground system is like a metro station, right? Metro system. In London, in UK, we call it underground. So essentially, it's a tube or subway system. So leaky cable are currently used massively in practical systems. So, and the length of that is like not just 10 or 100 meters, it's a kilometer. So it's an idea for outdoor. Okay, so so then you can also have this IoT using metal type. So that is very interesting as well. Okay, so that's all for generalized pinch antennas. Antenna placement. So this is based on this paper, not that paper. So okay, so from the research perspective or scientific perspective, I'm fascinated by this research problem, which is to decide where you're going to place or activate your antenna. I think that is a crown jewel for designing pinch antenna system, because different to conventional fixed location antenna system, for pinch antenna you can move it, you can relocate your antenna, right? So where are you going to put it? So that is to me is an important question. Yanqing did the first work, and it shows that this is a very challenging problem. Challenging because we can give this a simple example. So for example, you have two antennas, and then your effective channel gain essentially is the square of absolute value of the, because you have two paths. And then each of these paths is a complex exponential function. Your distance actually is in the exponent. Now, for complex exponential function, essentially it's cosine. It's a trigonometry function, is it? Cosine or sine. So cosine sine is a periodical function. That's the reason if you do optimization, you're going to have a lot of oscillation, local, well, not local. You're going to have a lot of quick, rapid oscillation for your objective function value. That's the reason a lot of people are using particle swarm algorithm or some heuristic algorithm or machine learning, because using convex it's really hard. The function is not that smooth. But that is a very interesting research problem, not really in other field. If you are good at this, then maybe you want to study. But we did something recently, this one. So actually during this GlobalCom, I had to spend a lot of time to revise, because the editor sent them yes, please.
Why exactly are we using particle swarm method?
Okay, so the question from the audience is why we using particle swarm algorithm. Now, it's because your objective function, whatever it is going to be a function of your effective channel gain. Your effective channel gain will be absolute value of the summation of multiple complex exponential functions. To make things even more complicated, your distance, which is or the location, your optimization parameter essentially is in the exponent. So you can say you want to optimize a function which is contains like a cosine x. Now x from 0 to 2 pi, you're going to have a full cycle. Then you have another full cycle. This is one cycle normally is related to wavelength. So that within just 1 centimeter, you already have a multiple periods. So that you're going to have quick, rapid oscillation of your objective function. Now for convex optimization, we really hate this type of function, because function is not smooth, right? And you have a lot of local minimum, local maximum. Now using a particle swarm, you don't really care about those oscillations. That's the reason that a huge amount of papers about using particle swarm or genetic algorithm, because indeed it's a very effective. Machine learning is this could also a very important application for machine learning, right? Is that okay? Okay, thank you then. Okay, so then we did a quick we did some study for because I like a closed form. I like some insight. So so that is one work we did. So for example, if you have two users, for some reason you can when we serve these two users in different time slots, then we fix our antenna, right? So then you can have three possible locations. One is for the position A is to ensure that the distance between user and this location will be the same as the distance between this location and the other user. Intuitively, I think this is the location should be chosen. It sounds like provide user fairness. And we found out this location never be used. You either use this location, which is the middle point between the projection of these two users on the waveguide, or you use you make the antenna close to one user. Okay, because I don't have time to go through the details, but the review actually I'm working on the revision. I just finished over GlobeCom. So one key question is about so the review. Sometimes the review questions are reasonable, so they really push us to do something with. Well, sometimes we're lazy, so then one review keep pushing, say you have to provide some insight. So now I think I have better understanding of this. But because time constraint now, I have to move on. Okay. Because I want to spend a bit more time for EDMA. So what is called the environment division multiple access. Because multiple access still in well, I mean, I think that is a fundamental problem for communication system. So what is multiple access? Essentially is a technique to use limited bandwidth resources to serve multiple users. During past, we have all these traditional multiple access. We have TDMA, which use time domain. You have FDMA using focus domain. You have CDMA using codomain. SDMA using spatial domain. We claimed NORMA is a new multiple access because NORMA use power domain, which actually conventionally this has not been used. Right? It's really hard to design a new multiple access because we want this new multiple access provide us a new domain for resource allocation. And it's really hard to find a new domain. That's probably the reason if you look around, although there are many new multiple access techniques proposed, but many of them don't really provide you a new domain. They essentially is a combination of existing ones. I mean, RSMA is very typical. It itself does not provide a new domain. Essentially, it's a NORMA power domain, and also you have to use beamforming or pre-coding. So that is actually SDMA. So you combine those two, you can serve users, right? So LDMA, that is in the near field, so called the location division multiple access. For near field, conventionally we have this angle domain, right? So for far field, you can you can differentiate the user or identify user in the angle domain for far field. For near field, we created this so-called beam focusing. That means as long as the user in this domain, we can also locate the user. Now, you have to use beamforming or pre-coding for LDMA, location dependent model. So it's essentially the SDMA. So I can go on and on. So we found out actually SDMA or MIMO is very powerful. Many multiple access actually can be reduced to SDMA. So that at the beginning, when we start this journey, we said, okay, we're going to design a new multiple access. And our first step, on purpose, we're not going to use MIMO. Of course, later you can use MIMO to improve your performance, right? But we're going to, on purpose, we're not going to use MIMO. We want to see whether, without using MIMO, can we design a new multiple access? So that is our motivation. With that, then we come to this called the environment division multiple access. Essentially, the domain is propagation environment, which is different to physical space. Okay, so for example, in this floor of academic building, all right, we have this partition. Let's think about it, if this partition, it could be, for example, a mirror, or could be see-through glass. For physical space, that's the same. We have something here. But for propagation environment, that's different, because if it is a mirror, there's a reflection. If it's like this, we have this probably fabric wall, then is absorbed, then there's no reflection, the signal cannot go through either. However, if the wall is this partition is made of see-through glass, the signal can get through that partition. So, in terms of propagation environment, also for it can be quite different. So that is something we want to use to realize the multiple access. Let's see some example that we can have better understanding. So for example, we can start with a very simple example of EDMA, simply by divide my surface area into multiple isolated regions. Now, these regions are formed by using by studying the propagation environment. For example, if I know that there are some structured obstacles, let's say I have some high or tall shelf. So in that case, for example, I want to serve these two users simultaneously, right? I can, conventionally, I probably should have placed my antenna at this place to serve both of these users. That actually is hard for multiple access perspective, because, for example, when this user is served, then the signal sent by this antenna to this user will also be picked up by another user. So in that case, you have so-called multiple access interference. However, if we know there's a blockage here, then I can, using pinch antenna, I can activate my antenna here, in the sense that the signal sent by this antenna will received by intended user. However, that signal will not cause interference to other user because of the blockage. Right. So we are using the environment, which is very unique, because conventionally, when we design multiple access, we focus on transmitter, we focus on receiver. Here, we look around, we use the environment. The benefit is following. So now each user can use all the bandwidths like SDMA, CDMA. Right? There's no time sharing or spectrum sharing. Sorry, there's no like each user can only use a small portion of time or frequency. Also, it is simple. Simple in the sense that there's no beamforming pre-coding multi-user detection. The signal sent by this antenna is very simple. There's no beamforming. I don't coordinate between these two antennas. So this antenna communicates with user, just send a single signal. And the user, when this user do detection, there's no multi-user detection. There's no MIC. There's no like normally we have a post pre-coding, right? So it's quite practical and simple. And also you can combine it with SDMA, MIMO, or NOMA, right? We are particularly excited because I think this is the moment to have this type of multiple access. The reason is nowadays, so I think many of you probably travel to Taipei for GlobalCom, and then you probably found out that we can say maybe half of the presentation or papers are about ASIC these days. So many papers about ASIC, right? Now, So the outcome of those RSAC algorithm essentially is a better understanding of the environment. However, at this stage, there's no clear understanding how this knowledge will be used. Of course, you can say this knowledge can be used for other disciplines, but then we will be used as a technician. We don't want that, right? We want our communication system can also benefit from those knowledge about the environment. Now, with EDMA, finally, you have the closed loop. So you have an ASIC, which generated the knowledge of the environment, that the environment can be fed back to your communication system to design your multiple access. Right? So then you can do, also you can use the EDMA to do ASIC, of course. Yes.
You assume that the environment is fixed, or you're also trying to program the environment, like using programmable walls and cutoff frequency.
Okay, so Professor Senka asked a very good question in the sense that because we're talking about environment division, right? That means are we going to program our environment? The answer is yes, we should. We should do that. The example we provide is passive approach. The example we provide here is we sense the environment, then I think in the long run we should. Yeah, for example, we can have certain partition, which is have a 3 mode of glass, right? Reflective, just then complete blockage, or observative, or see-through, like star rays. We can also have something like with some of our students were joking that you can have something like for the lamp. Normally you can have a cone, right? For the shade. Now you can you can also use this shade to control the direction. Not direction, control which area your antenna can focus. For example, for this antenna, if I apply a shade or cone, then to make sure that the signals will only cover a particular region and the other region will not be affected. So yes, so that's a very long answer to that good question. Should we reconfigure our environment? I think now this is the moment we should go that direction. Thank you then.
Sorry, very close to DLC concept.
So yeah, Professor Keshav asked basically asked this question. So this sounds very similar to VLC, which is absolutely right. So pinch antenna itself can be viewed as essentially is to achieve like a VLC. So you have a very, very good connection, last mile or last mile connection using the visible light communication. Pinch antenna is similar. We active antenna on top of that a user, so provide the good coverage. EDMA itself not necessarily relate to VLC, not necessarily even relate to pinch antenna. You can also use leaky cable. Leaky cable actually have an angle that can be used here. Okay, so I need to look at time. So okay, I think I'm going to skip the details. I'm going to skip the details. Okay, that's one thing I want to highlight, which is interesting about the optimization. Right. So naturally, we want to, no matter it's uplink or downlink, we want to maximize minimum of user's data rate with simple constraint. Why this is a very hard problem? Let me give you one example. Maybe some of you are, I mean, I'm sure many of you are very good, have a much stronger background in convex optimization than me. I know Professor Winket definitely do. So then I want to through this question, and then hopefully some will be useful to you. So this is one of the optimization problem we want to solve. Now, essentially, this two bracket essentially is something related to line side probability. a blockage probability, then you have this logarithm. You can see good thing for this optimization problem is that you have closed form expressions. So you can, it's not like some problem you don't even have closed form expression. You have you have to apply machine learning here. Technically, I think it's supposed to be simple, right? So each function is very simple. It's a very elementary functions. However, we have this product of exponential function with logarithm function. Then we actually, it's a non-convex, non-concave, so we stuck with that. And if you are good at optimization, then this is something maybe you can help, and that will be really, really nice. Because once this problem can be solved, that's open to the new world. There are a lot of things we can do in the following, but currently we are using SEA to approximate. It's a bit boring, and it's also suboptimal. Okay, I don't want to. Okay, let's talk about the more conceptual things. All right, then we can reserve more time for discussions. So pinch antenna is a new topic. There's a lot of interesting things can be done. So line side blockage, as we said, is a very interesting thing. Early we so this is one example. So conventional line side is bad, right? But in pinch antenna system is something very, very useful. For example, one antenna sending signal to another user. That if we do it carefully, without signal processing, beamform precoding, we can avoid the inter-user or cross-channel interference. Actually, this work actually led to EDMA. So we did this work first, and then that led to something EDMA. Okay. Yuan Wei is going to have another talk about pinch antennas tomorrow. He will introduce you that there are many tricks to, for example, you can control your not just phase, but the amplitude. What do we mean? So if I go back to the previous slide, I'm very sorry that I have go to that slide. No, sorry about this. Okay, sorry about this. So let's say, okay, so let's say you have two antennas on activate on a single waveguide. Now you can treat this as an analog beamforming. So because these two antennas essentially are sending the same signal, but with different phase. So essentially it's analog beamforming. Right? So before that work, that is our understanding. Using pinch antenna, we can realize analog beamforming. You can only really tune your phase. However, that work shows that Yuan Wei's work actually shows that you actually can tune. You can change your amplitude by, let's say this is your pinch antenna, by changing this distance or changing the width of your antenna. I think Yuan Wei is also going to talk about the multi-port theory. That will be useful to also further tune the phase and amplitude. Channel estimation. Now, the reason to ask this question is following. We said you can activate your antenna anywhere along the waveguide. That basically means there are infinity amount of channel steady information to be estimated. That leads to the question, it sounds like channel estimation is very challenging for pinch antenna. Actually, it's challenging, but it's not that hard. I mean, give you a simple, very silly example. If there's we only have line of sight communications, and everybody positions are fixed, there's nothing to be estimated because the channel essentially is decided by the location, and since locations are known, and there's nothing to be estimated. The problem is when you have this reflective non-line of sight. But in the end, so for example, Robert Schubert's group, they did something related to, they identify how many, you have only finite number, small number of reflective surface. Right? So then you can estimate that by using far field and near field things. near field, so which is very popular, still popular. Actually, the reason we studied pinch antenna is because at the time we were studying near field, and we find out that in this particular work, we found out that this so-called beam focusing, right? So to identify the user in the distant domain, we call it the resolution. It's not so good, and so it's mainly because conventionally the size of your array is cannot be too large, and however, so how to increase your the aperture of your or the size of your array, which because the larger of your aperture size of your array, the better resolution you will have. Conventionally, what you're gonna do, you're gonna use a comp, right? Or you have a distributed MIMO. Actually, one of the colleagues I met the day before yesterday during that workshop. So he's from Qualcomm. He asked a question: is pinch antenna related to DAS? I was thinking about, oh, what is DAS? Oh, it's a distributed antenna system, right? So I mean, so distributed antenna system is good, but then you have these issues actually with this backhaul. So because if you want to have a synchronization between time and phase synchronization between these distributed antenna, that's really hard. Okay, C-RAN, CF3, MIMO, they're along the same direction. So so then, okay, we can say pinch antennas at this stage will be the best way to realize near field communications, because the size of a near pinch antenna array is decided by your waveguard, and the waveguard can be very long, could be like 100 like 20, 50 meters. If I'm using leaky cable, that will be kilometer. So then you can think about that. Is really good for near field communication. I'm going to skip that detail. Another typical question about pinch antenna is how to activate this antenna. Are you really going to move your antenna? Now, to understand, we need to understand the question. People ask the question because they're worried. Moving an antenna takes time. Now, modern communications, high-speed communications, in the sense that within 1 microsecond, maybe like 100 or 1,000 bits have already been sent. Right? So response time to remove antennas is an issue. So that is related to we think the first way to the first step to implement pinch antenna is use this discrete way. For example, you have waveguard, and parallel to waveguard, you have a track. Of course, on that track, you can have a motor to move your antennas, but also you can that basically is a continuous movement. But you can also have a discrete way, in the sense that with a close pinch are very cheap. Then you can pre-install many close pinches on that track, and then during communications, real time, you activate those antennas at the position where you want. But of course, that will discrete antenna activation will cause some the optimality issue, because you cannot activate antenna anywhere you want, right? Then, but that's trade-off. Uplink basically. I think George actually his group did the first work in this region. So in the area that identified upbound. Now, constantly we have been asked the question whether there's a re-leakage problem. That means the following. So, for example, this user send a signal, and that will be picked up by this antenna. That signal will be passed along waveguard then arrive another active band antenna, will that signal will be releaked to free space? Some circuit design colleague told me that not it can be avoided by carefully designing your antenna, or but we want to have some simple, practical engineering solution. Right, so that leads to so-called the segmented waveguide. So basically, you have this waveguide. You put have multiple segments. Then in each segment, you have individual feet. That is good in the sense that, for example, if you use a signal is picked up by this antenna, then it will be immediately fed back to the base station. Then you don't have to worry about it will be re-leaked by other active antenna. So some of colleagues, they actually worked in those companies. Then they actually saying that, okay, base station has conventional antenna, massive antenna, and then you also have a pinch antenna. Are you going to let them work separately, or you should going to have a cooperation? I think that is an excellent question that lead to this direction, how to make sure these two type of antennas coexist. In waveguide propagation, in general, that there's a concern that in waveguide, you also have a propagation loss. And Yanqing actually did a serious work to show that this type of loss is not a big issue. It does not cause too much performance degradation. Even in my first paper, when we submit that paper, we did not talk about the in waveguide propagation loss. Then the review basically forced us to generate 5 new figures to show. But then we did, and it shows that indeed the loss, yes, there's a loss. But let's say this is a conventional antenna performance. This is a pinch antenna. Even there's a bit of loss, that the gap between pinch and conventional antenna is still very big. So I don't think that's a big issue. On top of that, if you really worry about the waveguide the propagation loss, there are many other ways to mitigate it. For one is this segmented. Sorry, where is that segmented? Yeah, segmented waveguide. So here the loss is just for short distance, right? So then you can avoid that in waveguide loss, or you can use a leaky cable, which use a lower frequency, sub 6 gigahertz. Then the in cable propagation loss is going to be very small. This is another exciting thing. I think I really appreciate Professor Octavia's invitation to this work. I think this is a fantastic idea, which opens door to the massive deployment of pinch antenna. So the motivation is following. Now, for Docomo's concept, the waveguide needs to be connect to the base station using cable. That is very awkward, right? Because if I have multiple waveguide, then you can think about it. There are so many cables flying around in the air. So this Y path essentially avoids that issue in the sense that you can deploy your waveguide anywhere in your cell, along the road, or in different part of buildings. Then using wireless backhaul to collect this connect this waveguide. So for example, one thing people have not done, I'm sure that is going to be very hot next year, is multi-cell pinch antennas. And then that leads to a lot of heterogeneous networks. You have a micro base station, and you have a lot of small cell base station. Small cell base station can use pinch antennas, and then then you have a wireless backhaul. I think that will be this concept of Y-path will lead to a complete whole new world direction. Very exciting. Other things, I think our the lot of things for next normal next generation model access, non-terrestrial networks, or vehicle ad hoc networks. ASIC, okay, so we also did something for ASIC. It's just it's a very we just want to show our community that this is a very interesting topic, in the sense that the use pinch antenna can offer 3 features. The first feature, or first property, is so-called uniform positioning accuracy. So if you place your antenna at the center of the surface area, right, but really depending on where your user is located, the position localization error can be completely different. In some place, localization, this is CLB, which is MSC, is very small. However, if the users unfortunately located in some place, then the MSC can be extremely large. However, using pinch antenna, you don't have that issue. Because antennas are distributed evenly in the surface area, you don't have that so-called geometric interpretation problem. Another property of pinch antenna assist ASIC is you have this conflict of communication sensing. For communication, I want to put my antenna on top of my head, because that provides the best communication link. But for some of us who work on localization previously, we know that that's a very bad position to place your sensor, right? Because you're going to have this geometrical interpretation issue. You want your sensor is a little bit off. So this bump actually is where your antenna is located. For sensing, which is CLB, is bad place to place your antenna. Another property is about flexible user-centric positions. So because we can, if we roughly know user is there, then I can massively activate a large number of antennas there, so that my accuracy is really good. Okay, so conclusion, I'm finishing. So first of all, I want to point out these online resources. So we built up this web page for pinch antenna. At a certain stage, I thought I can really manually provide this latest reference, but the speed of this research area is growing so fast that I think I could not update it quick enough. Also, we have a Q&A because when we did these talks, sometimes student or audience will ask various questions. Many of them are extremely good. So then here we have some questions. We provide our 2 cents for those questions. So you can go there and read if you have time. Now we just recap. We are excited. Sorry. To pinch antenna, because it's okay. Let's go to this. All right. So we are excited in the sense that Docomo indeed they provide this out of box thinking. When we don't have a line of sight, conventionally we just say, oh, there's no line of sight. Let's do fading. Let's improve that small scale fading. And Docomo said no. Okay, so let's create a line of sight. Right. So that is, to me, is extremely exciting. And also, this the solution is very practical. You saw that demonstration, right? It's such a neat and engineering solution. So there's no fancy concept like with a very complicated panel with many elements. And meanwhile, you can say pinch antenna has a very deep root in communication theory. In a way, you can say it's why is that the Qualcomm colleague asked about the difference between pinch antenna and DAS, or the distributed antenna array? Because in our mind, deep in our heart, we want to transmit close to the receiver. there are many other concepts that have been developed. For example, you have frequency reuse, CRAN, self-free, MIMO. Essentially, is to make sure that the transmitter is close to the receiver. But pinch antenna basically provide a very new and novel solution for that. Right? So I mentioned many papers, so you can download the papers and MATLAB code or Python code from, we have a GitHub homepage. If you want the slides, I think now Professor Kashev already have a copy of the slides. So you can either contact me or Professor Kashev to get the slides. All right. So with that, I conclude the talk. Thank you very much.
So, sir, you were discussing about multiple access techniques in pinching antennas, and two techniques which you were heavily focusing upon were NOMA and EDMA. So, when we consider NOMA in pinching antennas, and we are serving multiple users, so there is never an ideal case in communication. So, we always have successive interference cancellation error in NOMA. So, is there any way you are focusing upon eliminating that SIC error in NOMA, or you are mainly focusing upon EDMA for pinching antenna?
Thank you. Thank you. Now, in a way, you can say the reason we want to develop EDMA is in practice, as you said, we carry out SIC, there's a SIC error. Or there's and then in practice, you can also have a CSI error, channel state information error. That's just in the receiver, right? A transmitter, if you do beamforming pre-coding, you can have channel estimation error, which affect your performance. Even you have perfect channel, in practical system, when we realize the beamforming, we never use this idea beamforming. We use a codebook-based beamforming, which means mathematically these two vectors supposed to be orthogonal. But once you use those codebook-based beamformer vector, they are not going to be orthogonal, right? So all this actually motivates us thinking, can we have a system with a very simple transmitter, just sending one signal? A receiver, there's no SIC, simple like a maximum likelihood detection. No SIC, all right? So that is, I think EDMA can achieve that. You rely on your environment, propagation environment to cancel interference. For example, using this panel, I cancel my interference, right? So, of course, you could still have those in ideal scenario. Maybe you have interference, but you can analyze, optimize. Right. Thank you.
Any more question?
Yeah, thank you so much, Professor Zhiguo, for the wonderful presentation. First of all, I'm just thinking if we really need to change anything in the air interface. I mean, I'm thinking about the frame, for example, for 6G, the pilot, the synchronization, all that, and yeah, and how it will work with what exists currently. Yeah, well, that's something for the future, but I'm just wondering if you have any thoughts about that.
Thank you. Thank you. I mean, yeah, I think UMA later on is going to introduce a lot of sophisticated solutions, require a lot of beamform pre-coding. But if you look at my own work, many of them, I don't even use MIMO. I can use MIMO, make perform better. But I prefer those simple engineering solutions in the sense that, for example, if we use EDMA and you mentioned synchronization coordination between transmitters, right? Now, but if we know that this environment will cancel interference, and then coordination between these two transmitters is not needed. you only need to worry about the coordination between the transmitter and its associated receiver, not between other transmitters, not between other receivers. So the system overhead will be also reduced. It's all about how accurate we know the environment. But now I think we can be more confident. If 10 years ago we don't have ASIC, then we probably less confident. But with so many works about ASIC, I think we should be confident that the environment is the knowledge should be there, and we should be able to use that environment.
Thanks for sharing the interesting topic. And I have just a quick question. Can the pinch antenna coexist with MIMO? I mean, multiple spatial stream. Since currently I saw that there should have a line of sight between antenna and user. If I have multiple stream, how to use that? Since my multiple antenna system support also increase the spectrum efficiency.
Thank you. Both pinch antennas and EDMA can benefit by using MIMO. For example, early there's one example using pinch antenna to realize the up bound of MIMO, right? So that is basically how you can combine with MIMO. You can have a single or multiple waveguides, and now this is a very typical hybrid beamforming. So on each waveguide, you activate multiple antenna. That is analog beamforming. Between multiple waveguides, you have each waveguide has alpha chain. Then you have a digital beamforming there, right? So it's naturally compatible with MIMO. Yeah.
Even we can have multiple
Professor Wen's comment essentially, I'm just let the audience, the online audience know. So Professor Wen's question essentially is about MIMO. Very good at to use those small scale multi-pass fading. And so what happens if we use the pinch antennas? Okay, so my honest answer is following. This is not recorded. Okay, is that recorded? No, not recorded. Okay, that's good. So I mean, if we have pinch antennas, then in that case, maybe we don't really need to worry about. We don't really need to use those small scale fading, right? Okay. One audience ask about VLC. So if you have a VLC bulb on top of my head, there's no need to use MIMO multiples, right? A single bulb is not good enough. So I'm not saying MIMO is so you can still use MIMO even for nowadays. There are a lot of talks about MIMO with a line of sight. So if there's a line of sight, how to use the MIMO? Yeah, I think you can do that. So, but maybe in the future, if we can create a line of sight, then we can avoid use those small scale fading, because sometimes those models we use might not be very accurate. For the Rayleigh fading requires that you have rich scattering environment. But in many cases, we don't have that like infinite amount of scatters to create that infinite amount of summation, right? Then so that model might not be accurate anyway. That's a lot of things we can talk in for that.
Yeah. So I have one question.
Yeah. By the way, I really appreciate Professor Ketchup organizes a 1 hour and a half, right? That means I can talk 1 hour and we have half an hour for discussion, which actually is the most important part.
Yeah, so here each waveguide, and for each waveguide, we can have multiple pinching antenna. So, so what should be distance between two pinching antenna? Like conventional antenna is spacing lambda by 2, or can we keep more pinching antenna compared to conventional?
I think that first of all, we don't need to worry about the coupling, because for sure the distance between two pinch antennas will be larger than half of wavelengths, because your pinching will be large. So they cannot be placed very close to each other, right? Like less than half a wavelength. That's not possible. So specifically how far they should be, it's also dependent on how you're going to realize that pinch. Docomo's pinch is a close pinch. It's a very close one, right? So you also have the length of antenna itself, so that you can make it shorter, like narrow pinch. Then you can realize the shorter distance between two pinch antennas. So it's all about how you're going to realize that hardware, how can you realize pinch.
So maybe we can take 1-2 question from online audience.
Yeah, please. We have maybe this one. This one.
Yeah.
Maybe you need a multiplying function.
Okay, these are the questions.
Yeah.
Oh, okay.
We have some questions,
Okay.
so maybe some relevant.
Okay, thank you then.
Maybe for example, they save more.
Uh,
Several questions.
Okay, I'll start from the last, all right? So the last question is how to synchronize between pinch antenna moment and the user. So I guess this question is related to how to activate and pinch antennas. So you're talking about movement. So we it's not necessarily to move this antenna. You can simply just active antenna. So one of the slides we were talking about is there's a discrete activation. So that means along the waveguide you have you pre-install multiple pinches, and then let's say you pre-install 100 pinches, right? And when a particular user needs to be served, then you just activate that pinch at the particular point close to the user, right? So then that's the way you can synchronize between pinch antenna movement and user. Another question is, does the coherence time of channel affect with pinch movement? Okay, how to activate? Okay, so as long as I mean, I'm not a big fan to move antenna. Instead, I like a discrete antenna activation, because I think that is more accurate. You can move that. You can see many of these audience questions about movement. I think there's another direction called the move antenna. So all these questions actually also apply to that direction, which is headache. So using discrete antenna activation, you can avoid all these synchronization movement issues. All right, you can also avoid that.
Professor Ding, can I?
Yeah, please.
Actually, my question is that how to let us suppose a user can be at any place randomly. So how to like similarly to RIS, how to fix that location of the pinching antenna so that it will directly over the head of the user. So that is my question. That's why I'm asking about this movement of pinching antenna. because there is a variable for one variable should be common for the 3 coordinate system, Cartesian coordinate system, with the pinching antenna and the user. One coordinate must be same of any axis for the particular over the head deployment of pinching antenna. So as the Yuan Will Liu paper, the past tutorial paper, in which there are 2 to 3 type of location deployment techniques for the pinching antenna, like discrete, the one you said, and the other one like continuous or maybe mechanical, something like these kind of things. So since you're talking about the discrete deployment of pinching antenna, so how can we sure about that thing that the pinching antenna, that particular discrete pinching antenna should be over the head of that particular user? That's my question.
Oh, so actually, most discussions that we had are provided with assumption, by assuming that we know the user's the channel, which basically user's location. Then you will know where you should activate the antenna. So you need to know the location of the users.
Okay. And one more question regarding this, sir. When we are doing performance analysis of any pinching antenna, so on the user, similarly simple user, so is there any condition that one coordinate like X, Y, or Z of the pinching antenna, and similarly the coordinates of X, Y, Z of the user must be same, or they can be different at any like X1 is different for pinching antenna and X2 is different for user, or there must be one coordinate must be coincide with the pinching antenna and the user?
Okay, from the performance analysis perspective, right? So normally we assume that okay, so the X of antenna will be same as
Yes.
X of user, for a simple reason, because then you think about distance, that which is the difference between X and plus difference of Y, right? The difference X is 0. So as a result, then the number of parameters in your for your performance analysis will be smaller. So because X
Yes, sir.
that's the only reason.
That's the only. So so
You can use different locations. That's of course, but then you think about you have 2 additional random variables.
okay. So the location, that particular over the head location, it can be any angle to angle LOS, like from any top of the pinching antenna to any place of the room. It's not like it should be only at the perpendicular to the user.
It can be, but for performance analysis, you don't want to make your life too hard, right? You want to reduce the number of random variables. Because when you do integration, then you have less.
Yeah, but the only case, but why I'm asking that, because that is only for one research paper. But let us suppose if we have to location can any be location, because of the user can anywhere deployed in the room, maybe an angle to the pinching. So it is not necessarily that every time we have to put multiple waveguides or multiple pinching antenna specific that location. I'm asking about any practical way of doing that.
Yeah, I mean, so if we're talking about the performance analysis, that we normally to align antenna location with user location. If you want to use a different location, yes, it's possible. Then that is optimization problem. So you would you want to optimize the location of the antenna. All right.
Okay. Okay. Thank you, Professor Ding.
No.
Time's up. Okay. Okay.
Yeah.
Okay.
So
Right. Thank you very much. Then.
thank you, Professor Ding, for your nice talk. We have a small gift. So Professor Wen.
Hello, Professor Keshav. My last question is that in the chat also, that how full duplexing is possible.
Yeah,
can you please
okay,
shed some lights?
Yeah, I will discuss this question with him later, and I will let you know.
Yeah, over the email.
Yeah.
Yes, sure.
Okay.